Thank you for kind introduction. And first of all, thank you for giving me this opportunity to present a paper. And today, maybe you have heard about the CNF or cellulose nanofiber this term, but the preparation and the characterization of plant cellulose nanofibers and their application as new bionanomaterials to functional and commodity materials. Thank you. Yes. Outlined here first, backgrounds. As you know, the previous Professor Wada presented only plants can accumulate CO2 and emit oxygen. So we have to, net zero balance by 2050 for the CO2 emission and absorption. But but human beings and the plants also has to absorb oxygen to survive their lives and emit CO2. But only if plants can absorb the CO2 during the growing process, accumulating in the body as a plant components like cellulose, hemicellulose, lignin. So if we can suitably do this circular in our abundant forest areas, we can accumulate CO2 more efficiently. But as you know, the population is decreasing, and electronic media is much more popular than paper media. So we could not circle this system well. So if we can use about 50% of wood components or plant components to another new cycle, we can enhance the CO2 accumulation more efficiently. Especially, we have sufficient amounts of forestry. And then let's look at the hierarchical structure of crystalline cellulose microfibers. As you know, this is a tree, and you can see here, and wood tissue, and by separation of wood tissue, you can get single fiber to be used for paper and board production. And when you look at more the surface of fibers by more magnified level, you can see another more fibers called cellulose microfibers. So width around 3 nanometer, and these are bundles. And the one cellulose microfiber consists of 30-40 cellulose chains. However, in between cellulose microfibers, so numerous amounts of hydrogen bonds and also van der Waals forces are attached to each other. So far, we could not separate the cellulose microfibers to be used as cellulose nanofibers. But 2004, 5 or something like that, we have succeeded to completely individualize cellulose microfibers to individual fibers, nanocrystal fibers and networks or like this. The important point is that these materials are so large surface area. It's a third component. For example, the basic base polymer and the cellulose nanofibers. And the third component is a large amount of surfaces which can expect new approaches for material sciences. And so far, as you know very well, so many pulp and chemical companies are producing their own unique nanofibers variously, especially in the Miyagi Prefecture. Nippon Paper has started to produce so-called Tempo CNF cellulose nanofibers. It's the largest quantity in the world. Not only Nippon Paper, but also most of pulp and paper companies and chemical companies are also producing their own unique cellulose nanofibers. So we have decided it's already out of my hands. So we have decided separation of roles, R&D in industry for application and production technologies, while our laboratory for much more focusing on the fundamentals and advising. See, there are so many various cellulose nanofibers developed in Japan, primarily in Japan. And for example, you can see that most of them, by introducing their anionic charges efficiently just on the crystalline cellulose microfiber surface, you can individualize completely of the cellulose nanofibers, cellulose microfibers by these anionic charges. Especially, I believe that the other cellulose nanofibers are also safe to eat, but so far carboxymethylated CNF, cellulose nanofiber, has already accepted as a eatable materials already included in the foods, sweets, bread, or like this. Others are also, it takes, if you have to get some safety issue, it takes more than 10 years, 100 million Japanese yen or more, so it takes a long time. And roughly separated two categories. One is a chemically pretreated one. Our tempo oxidation is first developed one, and the next one is the others. Minus charges are introduced like this. And on the other hand, just mechanically fibrillation, also network heterogeneous structure, but you can get cellulose nanofiber materials without any chemical modifications. Then let's go to the fundamentals application of tempo-mediated oxidation cellulose and polysaccharides. When Professor Fuji may know my PhD work, but in that more than 40 years ago, I tried to chemically modify cellulose using organic solvent with large amount of chemicals and heating at 80 Celsius or more, 3 hours or more, or like this. But this is a tempo. Tempo is an abbreviation of 2,2,6,6 tetramethylpipridine 1-oxide forming this chemical structure. This tempo oxidation system was first developed in a group in Netherlands. They are trying to apply this tempo-mediated oxidation to starch foods. And I found this very advantageous point, completely different from my PhD work. It means you need not use organic solvent system, just aqueous system, catalytic amounts, small amounts, and highly residuous selective at C6 primary hydroxyl groups without any oxidation of secondary hydroxyl groups, and mild room temperature within 2 hours. So the tempo-mediated oxidation proceeds like enzymatic reaction in our living bodies, but proceeds more rapidly. So we believe it's 1996. We believe that this system must be an environmental friendly, sustainable chemical process, opposite to the conventional chemical reaction using organic solvent, chemical amounts of the chemicals like this. So we started this application of tempo oxidation to various polysaccharides from 1996, cellulose, chitin, cardran, aramidon, alpha-1,3 glucan starch, or like this, using the tempo-mediated oxidation. And expectedly, water-insoluble cellulose or chitin can be converted to water-soluble carboxyl groups containing or cellulose or chitin or like this. And also during this process, we found that by controlling the oxidation condition, you can get the nanocelluloses, nanochitin. And in the case of this catalyst was developed in, I forgot his name, but in Tohoku University, pharmacy, faculty of pharmacy. this adamantane tempo, you can get 2, 3, 6, 3 tricarboxycellulose. Of course, it's a water soluble. By the way, the mechanism is quite simple. Just tempo has this N plus structure, and the primary hydroxy groups are slightly dissociated, and because of the static hindrance, bind such structure, and first aldehyde structure are formed. Aldehyde are again hydration, and to form the carboxyl groups like this. And we found that the wood cellulose fibers, representative one is paper pulps. It's inexpensive, around 60 yen per dry kilogram. Is suspended in water in the presence of small amount of tempo and sodium bromide, and just starting the mixture after 90 minutes. First, we did not interested in at all, because the fibrous morphology are unchanged before and after the oxidation. Or must be, in this case, you can get the insoluble, water insoluble products can be converted to water soluble products. But in this case, original fibrous morphology is unchanged before and after oxidation. But carboxyl content increased almost 170 folds. It's a quite large amount of anionic charges introduced, even though the initial fibrous morphology are maintained. So we started this research from 2006, so 10 years later. Then this is a wood cellulose fibers, and the fiber width is around 30 micrometer. And the tempo oxidation, after tempo oxidation, the fibrous morphology is unchanged, but significant amounts of carboxyl groups are introduced. And once this mild mechanical disintegration, like magnetic stirring or blender or high pressure homogenization, you can get just such gel-like materials. And to begin with, we thought it's a oxidized cellulose are dissolving in water. No, in this case, not in the case. The TM microscopic observation showed that this gel consisting of the cellulose microfiber is the smallest element. The width is 3 nanometer, so from 30 micrometer to 3 nanometer is 1 to 10,000 smaller than the original fibers. And the mechanism of the nanofiber formation is just on the surface of cellulose. This is a glucosinate. Primary hydroxy groups are facing out, outside, inside, outside, inside, outside, inside. And by tempo-mediated oxidation, just on the just for the primary hydroxy groups facing outside are converted to carboxyl groups. So the original microfibers are tightly bound each other, but by tempo-mediated oxidation, anionic charges are densely, position selectively introduced just on the crystalline cellulose microfibers, resulting in the complete individualization of cellulose microfibers. And because we are in a graduate school of agriculture and life science, first we try to check all the terrestrial plants to see whether the microfiber widths can be the same size or not. Then it's a wood cellulose, it's a eucalyptus, chala, it's a sea algae, haircap moss, adiantum, rice husk, buckwheat husk. Almost all cellulose microfibers are the same with 3 nanometer. Must be produced biosynthesis using the same mechanism. But on the other hand, we also try to apply not only scientific matters, but also some applications with companies or institutes or like this. The reason why is that tempo oxidized cellulose fibers and also nanofibers has abundant sodium carboxyl groups, which can be converted to other metal ions or alkyl ammonium ions by simple ion exchange in water system. And switching of hydrophilic, hydrophobic properties can be achieved, like this one. And also scaffold for catalytic performance, like super deodorant performance. And also, have you ever heard of MOF? It's a metal organic framework, can be abundantly positioned selectively introduced just on the surface. And air filter performance, resistant to high humidity or such and such. And also the people expect that the highly strong, lightweight, transparent, and thermally stable composite with individually nanodispersed cellulose nanofiber elements in polymer matrix are possible to prepare according to high aspect ratio of charged CNF. You can partly replace all the petroleum-based polymers or metal compounds or like this. And also the key point is that not only the nanomaterial, nanofiber, nanocrystals, but also these nanonetworks and also even fibers, it's not cellulose fibers. It's a cellulose carboxyl groups abundantly containing new materials. So we believe that these materials also can be used for a new material science or industrial applications, especially when you coat the tempo CNF, just thin film on the PET film, the oxygen barrier properties dramatically improved, like this, because of no space in the fibers. Okay, and also very low efficient thermal expansion, because cellulose nanofibers consisting of the crystallized. Crystal do not move free, like so smoothly. That's the reason can be used as a lightweight electric board in place of the silica particles. Now our PC or smartphone contains so many electric board, but consisting of silica particles. It will cause the heavy weight. Anyway, application of CNF, it's already out of hand, but maybe you know the University Tokyo brand ball pen. It's a 380 yen. It's expensive, but smooth writing. Today I brought only 20 black ballpoint pen. I bought this ball pen by myself in our university shop. I did not request the company to freely, but anyway, so only 20. I did not expect that so many audience are here. So only, let's say, 20% can use this. I think you can distribute this. Yes, especially guests from Taiwan or very smooth writing. And very good, very interesting TV program is opened, but today it's time limited, so I could not explain details, but very smooth writing because of the cellulose nanofibers inside in there. It's a kind of shear shimmy or chikisotropy properties. And also University Tokyo Dorayaki, have you ever heard that? Unfortunately, I could not bring this one, but this is very good taste and usable carboxymethylated CNF are inside, and can be duration, lifetime is extended. The smooth texture is very good. So see, there's something like that. My name is here, so but it's not, honestly speaking. Almost no contribution to for this foods. But anyway, this is a regulation of the post plant germ, blood metabolic such and such. Anyway, bioactivity experiments can be done using the mice. And the tempo CNF, it's good. Glucose, blood glucose content decrease. Insulin content dramatically decrease. And GIP, maybe you know very well. Glucose-dependent insulinotropic polypeptide, also very, but insufficient nanofibers does not have such effect. Complete nanofibrillation is very important point. And also, the Kao company also collaborating our, and please, if you have time, please, this YouTube, I talked with this lady about how the tempo CNF can be contribute to the electronic materials and also the mobility. And another group, the US group, his group is very active, and they are proposing the solid kappa, solid state batteries, lithium solid batteries. They are proposing like this, and already started boosted venture company. And Nippon Paper Industry Crecia already reported this super deodorant diapers for adults to decrease helper's burden. And Mitsubishi, I explained this one. Mitsubishi Pencil developed CNF containing ballpoint pen, smooth writing, and the Taiyo Holdings, this one, and the Sumitomo Rubber, this tire, and the Kao Company, this one, and the Toyota. Maybe you have at least 2 or 3 Lexus, but I'm joking. Anyway. This metallic coating, cellulose nanofiber, our tempo CNF has been used already. And the Tohoku University, as a laboratory, developed the supercapacitor and this lithium and such and such. And one of our mission, collaborating with Shinshu University, is that maybe you know very well, that most of tires are synthetic rubber is used from oil, and also oil are converted to carbon black, and surprisingly 30 to 60% of the tires are consisting of carbon black. So all the petroleum-based materials, and you can get by abbreviation, small powders of carbon black are emitted to air, and some of them in our lungs. So our one of the goal is partly, not completely, partly CO2 accumulated biomass. So natural rubber can be partly in place of synthetic rubber, and the nanocellulose can be added in place of carbon black to form more environmentally friendly materials. And so far it's good results. Strength improved and no aggregation formed. And this work has been done collaborating with your Professor Jinnai Sensei of the Tohoku University. I'm not sure it works or not. You can see how the real-time TM images, how the deformation occurred. Just looks like the interface between the cellulose nanofiber and the rubber causing such deformation. Anyway, summary. We expect, based on the forest biomass resources unused, we have plenty of unused forest resources. So the converting the cellulose, and conventionally it's converted to paper and pulp, but partially using the charged group containing nanocellulose to apply the new materials. But these are a conclusion. It's a positive one. You can see in my slides in the desk. But of course, there are some problems or future challenges. Still, it's a promising material, but the quantity to be used as a commodity or frontier high technology materials is not so large quantity because the production amount is not so large, and the affinity between the hydrophilic cellulose nanofibers and the hydrophobic plastics are not so good. So sometimes you cannot get a homogeneous distribution of the cellulose nanofibers in the polymer matrices. Now, our laboratory started from 2020 as a university present divisions, and just a small laboratory with these members, and also the allowed members, only PhD students, Thai, China, Malaysia, and companies, supported by these companies. Others also are doing some activities. Thank you for your kind attention.